In this lesson, we'll go on to another important concept in chemistry, acids and bases. I would imagine that the majority of you have already been exposed to the pH scale and some of the general properties of acids and bases. So the only really new skill that we'll be working on is calculating the pH of a solution from the concentration of an acid or a base. This image illustrates the fact that the pH of a solution depends upon the relative amounts of acidic and basic components. So let's go and see what those are. So the basic properties of acids and bases. So for acids, they are going to taste sour. That's why I had a picture of a lemon, because lemons taste sour and they are acidic. React with metals to form hydrogen gas, provided they are in the right position on the activity series. They react with carbonates to form CO2 gas. You've done this reaction if you ever mix vinegar, which is sour, so therefore an acid, and baking soda, which is sodium hydrogen carbonate. And all those bubbles that you get when you do that are carbon dioxide bubbles. And they form electrolyte solutions. So that fact tells you that acids are capable of forming ions in solution, because that's what you need in order to form an electrolyte solution. Properties of bases: they feel slippery and they taste bitter. If you've ever gotten soap in your mouth, you know what I mean by the bitter taste and also what the slippery feeling is. They will react with some metals. Aluminum is the only one I can think of offhand. And then they also form electrolyte solutions. So we're going to go into how to name acids. There are two different types. We have binary acids, and the other type is called an oxyacid. With binary acids, notice it has that Bi for 2 in there, tells you that you only have 2 elements, so 2 capital letters. If you have a binary acid, the first part of the name starts with hydro. That just tells you that there's hydrogen in it. The second part of the name is going to be the root of the second element, so like say chlorine, and then you're going to chop off the "ene" part, kind of like when we were doing the nomenclature of ionic compounds, and change the suffix to "ic." So for example, HCl is hydrochloric acid. Now the other type are oxyacids. They're called that because they are the acidic form of all of those polyatomic anions that have oxygen in them. So they do not get a hydro because they have more than 2 capital letters. So the format is you're going to take whatever the root of the anion is and then change it according to whether you have an 8 or an ite. So if your anion ends in an 8, we're going to change it to an ic. So for example, HNO3, we ignore the hydrogen part. That has to do with the acid. And so we get our list of polyatomic ions out, and we see that NO3 is nitrate, which means that when it's in its acidic form, like HNO3, it's going to be nitric acid. And then if we look at, and if you have an ite, the ending changes to us. So in this case, we have NO2, which is the polyatomic anion nitrite, which means that the acidic form of it is going to be nitrous acid. So here are some examples of a whole bunch of different acidic acids. So we can see that they all have a hydrogen in the front, even this first one where it has these extra hydrogens in the middle. This hydrogen in the front, the reason why it's positioned there is because it's the one that's going to act like an acid. So these hydrogens that we have off in this first one, they don't participate. They're just part of the anions. So the hydrogens that appear first in the formula are called acidic protons or just protons. Sometimes I call them acidic hydrogens. And then notice that you can have different amounts. So we have single hydrogens for the first 2. We also have 2 hydrogens, so those would be diprotic. And we have one example up here that is triprotic. So monoprotic acid means an acid that only has 1 acidic proton, and a polyprotic would be an acid with more than 1 acidic proton. So notice that I have the second part of each acid underlined, just to make it a little bit easier to identify which part we need to be thinking about when we go to name it. So we're going to be looking at naming the anion and then coming up with the acid name. So we have the first one, C2H3O2, is acetate. 8's go to ic. So that means it's going to be acetic acid, which is what the sour part of vinegar is. It's actually like a 5% solution, so it's not very strong. And then we have NO3. We already saw that one. NO3 is nitrate, which means it's nitric acid. This is a component of acid rain. Then we have CO3. That's carbonate. And so that's going to form carbonic acid. And this is an acid that is present in carbonated drinks. It comes from the dissolution of carbon dioxide or the solvation of carbon dioxide in water. Next one is a binary acid, so we don't have an anion, so it's just going to be hydrochloric acid. That is the main component of stomach acid. And then next one, H3PO4. PO4 is phosphate. 8's go to ic. So it's going to be phosphoric acid. The reason why drinking colas are so bad for your teeth is because they actually have carbonic acid and phosphoric acid added to them. So the acid content is a lot higher. And then SO4 is sulfate. So that would be sulfuric acid. And that is the acid that is inside car batteries. Most of the car batteries these days are sealed up, so you don't have to worry about getting battery acid on your clothes. When I was growing up, if I had anything to do with fixing a car, which I did occasionally, if I got any of that sulfuric acid on my clothes would just dissolve. Not necessarily right away, but when they got washed, I'd end up with all kinds of holes in my pants, mostly. And then the last one, H2S, is a binary acid. So we know it's going to start with hydro. So it's going to be hydrosulfuric acid. It's actually only hydrosulfuric acid when you see it with an extra notation. Oops, need my pen. Where it says, oh darn it, I can't go back. When you see a notation of aqueous, and if it's just H2S and gas, then it's hydrogen sulfide, and that's also a really vile substance. All right, so when you have polyprotic acids, all of those acidic hydrogens do not come off all at once. So they are going to come off in a stepwise fashion, one hydrogen ion at a time. So in the case of phosphoric acid, we're going to go from phosphoric acid to dihydrogen phosphate and hydrogen ion. And then we have a second ionization where we have dihydrogen phosphate is going to lose a hydrogen ion to make hydrogen phosphate and a hydrogen ion. And then we have our third ionization where we lose that last hydrogen ion. This is kind of important to be thinking about because when you determine pH, it is the concentration of the hydrogen ions that are important, not necessarily or always related to just what the initial concentration of the non-dissociated acid is. So here's the pH scale. As you probably remember, if you have a pH of 7, that means it's neutral. If you have a pH below 7, that means the solution is acidic. And if you have a pH above 7, that means the pH is basic. The thing that makes it acidic, basic, or neutral has to do with the hydrogen ion concentration. Remember, those square brackets mean molar concentration, so moles per liter. So when it's neutral, the hydrogen ion concentration is exactly equal to the hydroxide ion concentration. If you have an acid, now the hydrogen ion concentration is present in a greater amount. And if you have a base, the hydroxide concentration is present in the greater amount. There are a set of equations that are very handy for calculating pH. The first one is that pH is equal to negative log of the hydrogen ion concentration. So we're going to look at an example. So what is the pH of a 0.15 molar solution of HCl? Get my pen this time. So we have HCl is going to break up into hydrogen ions and chloride ions. So if this one is 0.15, that means the hydrogen ions are also 0.15 molar. So we're just going to do negative log of the, trying to get this erased, 0.15. So, and we get a pH of 0.82. So next example, what is the pH of a 0.2 molar solution of sodium hydroxide? Now this one does not have an acidic hydrogen on the front, and our pH equation requires that we have a concentration value for the hydrogen ion. So what we're going to use instead is POH. Now this little p in the front just means negative log of whatever comes after it. So pH is negative log of the hydrogen ion concentration. POH is negative log of the hydroxide ion concentration. And then the last thing that we have is the relationship that pH plus POH is equal to 14. And this is true at room temperature. If you have higher temperatures, this shifts things around a little bit, but we're not going to worry about that. We're just going to do all of our pH calculations at room temperature. So going on to our example, if the sodium hydroxide is 0.2 molar, we've got a 1-to-1 relationship, so that means the hydroxide concentration is 0.2 molar. So that means our POH is equal to 0.7. So that means pH is going to be, it has to add up to 14, so we just go to pH is going to be equal to 14 minus 0.7, or 13.3. Now it's a really good idea to do a reality check when you're doing these pH calculations. If you're talking about an acid, and you know you have an acid, if it has an H in the front like that, then you should get a low pH. If you're talking about a base, and bases are going to be a metal with a hydroxide on the end, not with a hydrogen in the front, you should get a high pH. So if you just did this first negative log and weren't thinking about it, you should be able to catch the fact that a pH of 0.7 doesn't make any sense for a base. Now we're going to be talking about two different models of acids and bases. The more simplistic one is called the Arrhenius model, and next lesson we'll go on to a more general model. So in the Arrhenius model of acids and bases, an acid is any substance that contains acidic protons that will ionize in water to form hydrogen ions. So here we have hydrochloric acid ionizing to form hydrogen ions and chloride ions. We also have sulfuric acid going to form 2 hydrogen ions for every 1 sulfate ion. So we're going to practice doing some more pH calculations. So if we have a 0.1 molar solution of hydrochloric acid, that means we have a 0.1 molar solution of hydrogen ions. So that means our pH is going to be equal to 1. If we have a 0.1 molar solution of sulfuric acid, because we have a 1 to 2 relationship, that means that our concentration of hydrogen ions, and we're going to assume, for people that know a little bit more about this, that both of these hydrogen ions come off completely, ionize completely. So it means that the hydrogen ion concentration is going to be equal to 0.2 molar. So we do pH calculation and we get a pH of 0.7. So we have twice as many hydrogen ions, we get a lower pH. So that makes sense. So a base contains hydroxide ions. Typically it's a metal, group 1 or group 2 metal. with hydroxides that will ionize in water to produce aqueous hydroxide ions. So here we have sodium hydroxide and magnesium hydroxide ionizing to increase the concentration of hydroxide in the solution. All right, so if we want to find the pH, we don't have hydrogen ions present. We have a bunch of hydroxide ions present. So that means we're going to have to find pOH first. So we have a 1-to-1 relationship. So our pOH is going to be equal to negative log of 0.1, which is 1, which means our pH is 13. It's in the basic range, so that makes sense. Then we have magnesium hydroxide. So this is a 1-to-2 relationship, so that means our concentration of hydroxide is twice as big, so 0.2 molar. So the pOH is 0.7, and the pH is going to work out to be 13.3. So some more examples. We have a solution has a pH of 2.5. What is its pOH? Remember, we have that really nice relationship that pH plus pOH is equal to 14. So we're just going to go 14 minus whatever the pH was, and we get so 14 minus 2.5, and we get a pOH of 11.5. So the next one says a solution has an H plus concentration of 1 times 10 to the minus 3. What is its OH concentration? There's actually two different ways to calculate this, but I'm using this technique because it's a little bit more straightforward and it doesn't involve using an excessive number of numbers in scientific notation. So the first step, you find the pH. And then you say, all right, well, it's negative log of 1 times 10 to the minus 3. One of the checks that you can use is that whatever your pH is, or pOH, it's going to be close to whatever that power is on the 10. I used to think that's what the little p stood for, was power of. It's actually potential. It's an electrochemical term. But it's an easy way to estimate it. And so, sure enough, yeah, pH equals 3. Then we're going to subtract from 14 to get pOH. The way you undo the little p function, it's going to be, in the case of finding hydroxide, it's going to be 10 to the minus pOH. If you wanted to find pH from find H plus from pH, it'd be 10 to the minus pH. And these equations are all in your reference packet. So then we plug the number in. So it's going to be 10 to the minus 11. So in proper scientific notation, it would be 1 times 10 to the minus 11 molar. And then the last one, a solution has a hydroxide concentration of 1 times 10 to the minus 2. So you say to yourself, all right, I'm going to estimate this. So that means the pOH is going to be close to 2. And it is exactly 2 because that first part is a 1. So now we know our pOH, subtract from 14, and we'll get that the pH is 12. All right, so wrap up. The Arrhenius model says that acids produce hydrogen ions in water, and bases produce hydroxide ions in water. We kind of had a review of the general properties of acids and bases. The key ones are that acids taste sour and react with carbonates to form carbon dioxide gas. And then with bases, they feel slippery and they taste bitter. Nomenclature, we saw that there are two different types of acids. We have binary acids, so 2 capital letters in the formula. When you go to name those, it's going to be hydro is how it's going to start. And then it's going to be the root of the second element, so chopping off the INE typically. And we change that, and then we add an ic. So for example, HCl is hydrochloric acid. Oxyacids are where we have a hydrogen, you have the acidic form of one of the polyatomic anions. So it's really important to identify the polyatomic anion because you're going to have to use its name in order to figure out how the oxyacid's name ends. So if your polyatomic anion ends in 8, we change it to ic. So we saw that with nitrate. If you have the acidic form, it's going to be nitric acid. And then if it ends in ite, it gets changed to an us. So that means that if you had HNO2, which is NO2 is nitrite, so that would be nitrous acid. Key thing there is that oxyacids, their names do not start with hydro. We saw that there are 3 relatively easy calculations to use when you're talking about these kinds of simple acids and bases. So if you have an acid, you can find the pH directly, negative log of whatever the hydrogen ion concentration is. If you have a base, you have to find the pOH first and then subtract from 14 to get what the pH is, because people don't talk about solutions in terms of their pOH values. And then what I've been talking about so far are all strong acids. They make the math easy because they ionize completely, which allows us to use the concentration of the initial acid that you have to use that concentration directly to find H plus or OH minus. In the next lesson, we'll be looking at how to find pH or pOH if you have an equilibrium involved with your acid or base dissociation. So look forward to talking at you next time. Thanks for listening.